Hello, Doctor.
Yes.
Can I ask you quick questions about the project?
Yes.
Now, for the progress report to be submitted today.
I extended that date, honey.
Oh, okay. No, not about the date. I wanted to ask you, other than the four questions that we need to answer, do we have to include something else like introduction, discussion, problem statements?
You can make it, like if you want to, because the report should be like a normal report that usually you submit in other courses, honey. Similar to that, honey. So it should have like actually, the title, the project details, and some basic introduction about the work. So not in much detail, but those things you can give any like in short, any. And mostly it should be like focused on the work that has been given, the tasks that are provided there.
Yes. Okay, thank
Okay.
you.
So for the when you operate the control rectifier in inverter mode, we call it line commutated converter. We call it line commutated. Okay, at the end of the lecture, if you have some questions about the midterm exam, we can discuss. Okay, so let us first finish this chapter and then we can discuss. So what happens that when you operate the converter as a rectifier, it converts AC power to DC. It converts from AC to the DC side. It converts AC power to the DC power. And the delay angle should be less than equal to 90 degree for this. Now, if you increase the angle above 90 degree, then this start pumping power from the DC side to AC side. Okay, it start pumping power from DC to the AC side, and that is called the inversion mode. So it is acting as an inverter. So we call such inverter as line commutated converter, because this is the converter that is operating from the now from the power is being fed from DC side to AC side. It is called line commutated converter, and the angle at which it operates is more than 90 degree. So, and how it changes the power? By changing the voltage polarity. Not by changing the current. Current remains the same. That means the current is flowing in one direction. It keeps on flowing in one direction. And as you know that in case of a thyristor, the current can only from anode to cathode. It only flows from anode to cathode. It does not flow in the reverse direction. So the current direction will not change. The voltage polarity changes. So at the load, the voltage polarity, when it was before, it was plus and minus. Now it becomes minus and plus. So when the voltage polarity changes, then the power becomes negative. When power becomes negative, that means it is no more acting as a source, but it acts as a load. It is no more as a load. It acts as a source. So it is pumping power back from the DC to the AC side. So what you see here, that if you fire the thyristor at alpha is equal to 150 degree, so it start conducting from here, and the output voltage, it will give like this. Okay, and then the next thyristor is turned on here, so this will be the output voltage. So what you see that the average output voltage is negative. It is negative. There is small portion positive, but overall it is negative. So the voltage become negative. So the power is not transferred from the DC to the AC side. Okay, and this was the problem that we have already seen. So just a quick recall. Now, let us see the half wave control rectifier. This is called half wave control rectifier. So half wave control rectifier is like this. So half wave control rectifier, you have three thyristors. And they are connected to three phase. They are connected to three phase supply. And their cathode is common, and the load is supplied like this. Okay. So this is the half wave control rectifier. Now you see, since the thyristors, all of them are having same cathode. So when they will operate, when this anode will be most positive, when the anode is most positive. So this is the three phase that we see, that this is the three phase that is applied to the thyristor. So from this point to this point, we see that phase A is most positive. From here to here, phase B is most positive, and from here to here, phase C is most positive. I write here R phase, B, yellow phase, and blue phase. Okay, you can call it A, B, and C phase. Okay, so we see that from this angle to this angle, in this duration, phase A is most positive. So any thyristor that is connected to phase A will operate in this region. Any thyristor connected to phase B will operate in this region. Any thyristor connected to phase C will operate in this region. Clear? So we measure the angle alpha from here, from this point. This is called alpha is equal to 0 point. This is called alpha is equal to 0 point. So actually, you see that it is voltage angle 30 degree, but alpha is equal to 0 degree. Okay. So at 30 degree, because this is sine omega t, VA is Vm sine omega t. Okay. So at 30 degree, it is half Vm. So at this point, because we cannot operate at this point, at these points, we cannot operate because these points is lower voltage. Only at this point afterward, the voltage of phase A is high. So this point is called the reference point. This is called alpha is equal to 0 point. This is called alpha is equal to 0 point for phase A. And this is alpha is equal to 0 for phase B. And this is alpha is equal to 0 for phase C. Okay. So if you operate phase A or thyristor A, when thyristor A is operating, so thyristor A is operating, the other thyristors are off. So this is how the switching diagram will look like. So what will be the voltage across the load? It is VA, and this is your neutral point. So this is your VAN that will appear across the load. So the load will have the same as your voltage A, source voltage. So VA output voltage or the load voltage is same as source voltage when that thyristor is working. Okay. So when this is operating, when this is conducting, VA will be across the load. When this thyristor is operating, the other two will be off. So VB will be appearing across the load. When this will be operating, VC will be appearing across the load. Okay. And what is the voltage that will appear across the thyristor itself? So when it is operating, voltage will be 0 ideally. And when it is not operating, what is the voltage that it is coming across this? So that we have to check. Yes. So that we have to check. So now see here, for alpha is equal to 0, what is the voltage across the load? Voltage across the load will be same as the source voltage. So I will draw like this. from here to here. From here to here, this is the voltage at the output. Then when the next, from at this point, what will happen? The thyristor 2 will be turned on, or phase B will be turned on. So this will be the output voltage. This will be the output voltage. It will follow the source voltage. So source voltage is now highest is VB. And then at this point, alpha C will be triggered, or thyristor C will be triggered. So the output voltage will be same as your. Okay. Do you understand this point? If you have any question here. So this is how the output voltage looks like. So what is the peak value of the output voltage and what is the minimum value of the output voltage? So what is the minimum value? This thing. This is your minimum, which is equal to nothing but 0.5 Vm. That is the minimum. And what is the maximum? Maximum is the same as the phase voltage peak value, which is Vm. Same as the phase voltage peak value. Any question here?
Yes, doctor.
Okay. Now, can we draw the output voltage when alpha is different? When alpha is different. So what is the voltage? Suppose at 30 degree. So when we start at alpha is equal to 30 degree, when we say alpha is equal to 30 degree, so that means you count from here, you start counting from here. And when you count from here, this is equal to 30 degree. This is 30 degree. So the output will be from here. So this is 30 degree. Here S1 will be on. Then here SB will be on. And here SC will be on. So this is my output. Now, this will go here. This will go up to this point. This will go up to this point. Yes. So when this will, and then from here onward, you see, you get the phase B, and from here onward, you get phase C. This is what you get as the output. This is what you get at the output. Understand?
Yes, doctor.
Okay. Now let us see what will happen if you have alpha is equal to 60 degree. 60 degree. So we start counting from this point. So where will be my 60 degree? This is my point for the 60 degree. That means SA will be on here, SB will be on here, and SC will be on here. Okay. So now what will be my output? You see, output will be this. It will come like this. And now when you come to this point, it will go in the negative direction also. It will go in the negative direction also. But look, if you have only resistive load, if you have R load, it cannot go negative. So where it will stop? It will stop at this point. And then it will give you 0. And then it go here, and then it will come here, and then it will be 0, and then it will be like this. It will be 0, and then it will be like this. So this is discontinuous mode. This is discontinuous mode if you have resistive load. But what happens if you have RL load? If you have RL load, then it will go in the negative, no problem. It will go in the negative. So it will go in the negative direction like this. It will go in the negative direction. Do you understand this point? What kind of load if you have resist? Yes.
Yes, doctor. For alpha equal to 30, we went beyond, even if it's not the highest voltage. SA, the thyristor connected to SA will still be conducting even if it's not the highest voltage.
No. It will conduct when it is highest voltage. And you see here for 30 degree, for 30 degree. Yeah, you mean, and okay, understand your question now. Okay, so you see here what is happening, that you start your conducting at this point, but it will keep on conducting here. It will keep on conducting. Now at this point, as you said that this will be on, yes, but you did not trigger. You did not trigger. You understand? You did not trigger your next thyristor. You did not trigger your next thyristor. When you at this point you will trigger your next thyristor. And as you know that even if the voltage across them is high, but if you do not apply the gate pulse, it will not operate. So which will operate? It will keep on conducting. It will keep on conducting until this point. It will keep on conducting until this point. When you trigger the next at this point, then it will start conducting the second. Do you understand this point, Hane?
Yes. Now I
Does I
understand.
answer your question? Yeah. Okay.
Yes.
Yes. Yes. Any other question?
Doctor,
Yes.
Doctor, why when we begin from alpha equal 30, it starts conduction on the 60 degree and same for others?
Yes. 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 Hane. You see here, I told you that this is the point of your reference. This is your reference point. Okay. This is called alpha is equal to 0 point. So whenever you count alpha, you count from here. You count from here. Okay. You count from here. You do not count from 0. You do not count alpha from here. This is not your reference point of alpha. Your reference point of alpha is this. So the reference point of alpha is itself at 30 degree of the sine wave. Because at this point only, your RA is more than your phase A is more than the other voltage. So you cannot operate your RA at this point. You can operate only your SA after this point. And you can operate your phase B only after this point. You can operate your phase C only after this point. And that is why this is called alpha is equal to 0 point. This is called alpha is equal to 0 point. So when counting 30 degree, it will be actually at 60. It will be actually at 60. This is called 30 degree angle. Okay. Don't confuse with this 30. This 30, no. This alpha, you have to look at the alpha. Alpha is equal to 0 is at this point. This is the alpha is equal to 0 point. Does this answer your question?
Yes, doctor, thank you.
Okay. So you see, this is called a two-quadrant converter. This is called a two-quadrant converter. Why it is called two-quadrant converter? Because you can get positive output voltage, you can get negative output voltage, but the current direction remains the same. Current is only in the positive direction. Okay. So this is called two-quadrant converter. This is called two-quadrant converter. It can have positive output voltage, it can have negative output voltage, but the current is always positive. Okay, flowing in one direction. Now, what happens when you have 90 degree, your alpha is 90 degree. When your alpha is 90 degree, where you will start? You will start operating here. This is your SA point, and this is your SB point, and this is your SC point. This is at alpha is equal to 90 degree. Now you have to check if you have RL load or if you have R load. If you have R load, then it will start operating from here, and then it will finish at this point. It will finish at this point, and then it will be 0, and then it will go like this. Okay, if this is R load. But if it is RL load, it will go in the negative. It will go in the negative. Okay. Now, what is the limit of alpha? At what alpha? After that, we cannot operate. So you see, this is the point. Alpha should be less than 120 degree. Alpha should be less than 120 degree. After that, we cannot operate. Because your positive thing is finished, no more. Okay, the dominance of A is no more there. So this is for alpha is equal to 30 degree. You see, this is my operating point. So I will move like this, and I can draw my output voltage in this way. This is my output voltage. For alpha is equal to 60 degree, my operating point has shifted here. So I get this. If it is RL load, I will go in the negative. If it is R load, I will not go in the negative. I will be only having positive. So this is my output voltage. Okay. The same thing is drawn here. Now you see, when you have alpha is equal to 90 degree, then you have equal positive and equal negative. So your average voltage will be 0. Okay. Here your average voltage will be positive. here your average voltage is positive. But if you go beyond this point, then it will be negative. That means the operating as an inverter or line commutated converter. Now, if you have freewheeling diode? What if you have freewheeling diode? Now, so you see, suppose you have like this. Just assume one half-wave rectifier. This is called freewheeling diode. This is called freewheeling diode. So when you turn on this is my sine wave. So say this is my alpha. This is my alpha. So at alpha, I operate, I get this voltage. Now, as soon as I start going in the negative direction, as soon as this become minus and plus, this diode will be turned on. This diode will be turned on. So this diode will be turned on because your source voltage is now reversed. So when this will be turned on, then what will be your output voltage? Output voltage will be 0 because this is operating, so output voltage will be 0 ideally. So this will be your output. Okay. So the same thing is showing here. If you have, what happens if you have a freewheeling diode? So suppose if you have a diode connected here. So if you have a diode connected here, then it will not go in the negative. Even if you have RL load, it will not go in the negative. It will short at this point. Because as soon as this gets negative and positive, it turns on. It turns on the diode. So this is what is shown here, that all the time you see, for alpha is equal to 30 degree, freewheeling diode will not operate. There is no issue. There will be no problem. But as soon as you have alpha is equal to 60 degree, what happened that the freewheeling diode has start conducting and you will get 0. Okay. So there will be no negative. There will be no negative if you have freewheeling diode. There will be no negative in it. Because as soon as it start negative, the freewheeling diode will turn on. So now let us see what is the output voltage. So output voltage is given as 1 upon T, the total time period. So what is the time period? You see, you have 360 degree total, 360 degree in one cycle. And how many thyristor you have? How many thyristor you have in half wave?
3.
3. So each one should conduct for
120.
each one should conduct for 120 degree. Each one should conduct for 120 degree. So each one will conduct to 120 degree. So this is your time period is 2 pi by 3. 1 upon 2 pi by 3 is your time period. And what is the point at which it start conducting? It start conducting at 30 degree plus alpha. And at what angle it finishes? It finishes at 150 plus alpha. You see here? This is what you see here. It start at this point. It start at this point, which is nothing but 30 degree of the sine wave. So 30 degree of sine wave plus any angle alpha. And at what angle it will finish? It will finish at this point, which is 150 degree. 150 degree plus alpha. So that is what you see as the limit. Okay. So 30 degree plus alpha to 150 degree plus alpha. When you integrate, you get this 3 V line to line peak divided by 2 pi into cos alpha. And if it is full wave rectifier, we will see that this 2 will finish. It will be 3 line to line peak value divided by pi. Okay. VLM is the peak of the line to line voltage. So if you have line to line voltage 415 volt RMS, then VLM will be 415 times root 2. That is the peak value of the line to line. Okay. Now, if you have freewheeling diode connected, then the starting point is okay, but the finishing point will always be up to 180. It cannot go beyond that. It cannot go beyond that. You have to limit at 180 degree. Okay. So limit here is given as 180. So from here you will get the 1 plus cos alpha. You will get 1 plus cos alpha. Where is the formula? with freewheeling diode. Yes, this is the freewheeling diode with freewheeling diode. I think this is, I don't remember, probably this is 3 VMLM by 2 pi 1 plus cos alpha. This is what I think. I don't think this is 30 degree. I have to check if it is 30 there or not. Anyway, now we'll go to the 3-phase full bridge control rectifier. Yes.
Doctor, is it VM or VLM? In the formula, it's written VM.
No, this is. Wait. This is half-wave rectifier. Half-wave rectifier. So it should not be line voltage, because here what comes is the phase voltage that comes. Yes, you are right. Because here in the output voltage, this is phase voltage. This is not line. This is not line. I think there is an error here. I think this is error here. And I have to check for the half-wave rectifier. I think this should not be line. This should not be line, because we do not get line voltage. We get cos. We get, yeah. You're right. Because you see, this is VM, and it will be VM. It will be not line, because this is half-wave rectifier. So in the half-wave rectifier, we do not get line voltage. We only obtain output as phase voltage. So it should not be line. It should be P of the phase. 3 into VM upon 2 pi into cos alpha. This should be the answer. Okay. I don't think this is correct, honey. No, this is not correct, honey. I will make correction here, honey, in this slide, honey, because this cannot be line, because we are getting only the output voltage as phase. We are not getting line. Okay, we are not getting line. So that's why you see here it is VM, honey, but also I have to check about this 30 degree, honey. Okay.
Professor, I got a question, if
Yes.
you don't mind.
Yes.
If you can go back a slide. Does it matter here that it says it's a star-connected transformer? Because the line-to-line voltage should be the same as the phase voltage in a star-connected transformer.
No, it is in the delta connected, they are same, not in the star. In the delta connected, they are same, but not in the star. Star, their line and phase are different.
Yeah, true. Thank you.
Okay. Yes.
Doctor, can you kindly go to the next slide? Here, why can you kindly clarify from the graph why 180?
Yeah,
The
because
limit.
you see here. Yeah. You see here. This is, if it is the if you have freewheeling diode, then at this point, as soon as it reaches this point, you will not be able to go beyond this point. Okay, you cannot go in the negatives. The maximum that you can go is 180 degree, up to 180 degree. You see here, this was the same as at 30 degree. You see, when alpha is equal to 30 degree, we reached up to this point. Okay, that which is equal to 180. Now, if we do not have any freewheeling diode, and say I have 60 degree, I go beyond this. You see, I go beyond this. I reached up to 210 degree. I reached up to 210 degree. But suppose there is a freewheeling diode, then what will happen? Freewheeling diode will start operating from this point to this point. So as soon as we are reached 180 degree, freewheeling diode will turn on. Freewheeling diode will turn on, because after 180, this become minus and this become plus, the source voltage. So this will turn on. So in the maximum that we can go, if you have freewheeling, is up to 180 degree. We cannot go beyond that. But if there is no freewheeling diode, we can go more. You see, we have gone up to 210. Even we can go up to more than this. Okay. If it is RL load, certainly if it is RL load, if it is R load, then of course R load also we cannot go beyond 180 degree. for R load. So either you have R load or you have freewheeling diode. In both the case, the maximum voltage that you can go is up to 180 degree. Because as soon as you go up to 180 degree, freewheeling diode will pitch in, will be turned on, and your output voltage becomes 0. Do you understand this point?
Yes, doctor. Thank you very much.
Okay. Now let us see here. This is called three-phase full bridge control rectifier. So three-phase full bridge control rectifier, you have 3 thyristor in the upper group and 3 thyristor in the lower group. So 3 upper group and 3 lower group. And how we number them? 1, this is number 1, number 2, number 3, number 4, number 5, number 6. And why we sequence like this? Because this is the sequence of their turning on. This is the sequence of their turning on. So when you turn on 1, after that you have to turn on number 2. After that you have to turn on number 3. Then you turn on number 4. Then you turn on number 5. And then you turn on number 6. Always it will follow like this. Okay. So that's why we number them like this. Okay. Now, how many thyristors are there? There are 6 thyristors. And what is the total angle in one cycle? 360 degree. So how many degree one of the thyristor will operate? 360 by 6. That means 60 degree. So one thyristor will operate for 60 degree. This will operate for 60 degree. Then 60 degree, 60 degree, 60, 60, 60. So that 6 thyristor will operate in 360 degree. Do you understand this point? So the conduction angle in half wave was 120 degree. One thyristor was conducting for 120 degree. But in full wave, thyristor will conduct only for 60 degree. Thyristor will conduct only for 60 degree because there are 6 thyristors and you have to accommodate 6 thyristors in one cycle. So each thyristor will conduct for 60 degree. Okay. Now, in your book, they have given only this diagram, which is not sufficient to explain the operation of full bridge. I will explain you with more graphs. Okay. Now, let us see what happens here. That each time you will see that 2 thyristor will conduct. Each time 2 thyristor conduct. One from upper group and one from lower group. So you will see that 2 thyristor will conduct at one time, one from upper, one from lower. And what is the angle for which that they will conduct? They will conduct for 60 degree. Each one will conduct for 60 degree. Each one will conduct for 60 degree, and at any instant of time, you will see that there will be 2 thyristors that will be conducting, one from the upper group and one from the lower group. Now, exception to this will be, you will see that when you will have the impact of the source inductance, then you will see that 3 thyristor will conduct. Okay, 3 thyristor will conduct at one time. If you include the impact of the source inductance, that we will discuss later. Now, moreover, so this is point number 1. Point number 1, that each thyristor will conduct for 60 degrees. Point number 2, 2 thyristor will conduct in each cycle, in each instant of time, one from upper group and one from the lower group. Now, third point, when your one is conducting from here, one is conducting from here, and one is conducting from here. Okay, what is the voltage that will come across the load?
Line
You
voltage.
see, yeah,
VAC?
this is C. So VAC will come across the load. So line voltage will come across the load. So every time line voltage will come across the load. In half wave rectifier, phase voltage will come across the load. But in the line voltage will come across the load when it is a bridge rectifier, full wave bridge rectifier. Okay. This is point number 3. Moreover, you will see that the direction of current always remains the same. Always remains the same. The voltage could change, polarity could change. Okay. Moreover, what you see that if your inductance is very high, then this current will be not having any ripple. It will be like constant. This is your DC current. Like this. If your inductor of the load is high, then you will have not ripple. But if you have less inductance, what you will see? You will see current like this. You will see like this. It has ripple. And what is this ripple? This is called peak-to-peak ripple. This is called peak-to-peak ripple. And what is the harmonics that you see here? In the full wave single phase, you have seen it was 2, 4, 6, 8 like this in single phase. But in 3 phase, it will be 6, multiple of 6, 6, 12, 18. This harmonics you will see. Okay, this you will see. Understand the ripple in the current. Now I will explain you important concept of drawing the output voltage. How to draw the output voltage. Okay, so to draw the output voltage in a full bridge control rectifier, we need the phase voltage waveform as well as we need the line voltage waveform. Okay, so this is my phase voltage waveform, and I explained you in the last class how we draw the line voltage. There are 6 line voltages. VAB, VBC, VAC, VCA, VBA, and VCB. These are 6 voltages. Okay, there are 6. This is VAB. The inverse of this is VBA. This is VAC. The inverse is VCA. This is VCB. The inverse is VBC. Okay, so there are 6 voltages. As you can see that from the phasor diagram, if this is your VA and this is your VB and say this is your VC, then you can draw 6 line voltages. You can draw 6 line voltages. So you see, we have 3 line voltages, but there are opposite to that also. Okay, so we have shown it like this. There are 6 line voltages, and you know that the line voltage leads 30 degree the phase voltage. Yes. Okay. Now, what I have done, I have drawn 3 phase voltages ABC, and correspondingly, I have drawn 6 line voltages. VAB, VAC, VBC, VBA, VCA, VCB. This is exactly drawn from this, from here. From the phase voltage, I have drawn the line voltage. Okay. How? By just using this relation. You have VA is equal to VM sine omega t. VB is equal to VM sine omega t minus 250 minus 2 pi by 3, and then VC is equal to VM sine omega t plus 2 pi by 3. This is my phase voltages. Now you can find the line voltage. VAB as VA minus VB. VBC is VB minus VC. VCA is equal to VC minus VA. Yes, and then you write the expression for voltages and you obtain the expression for the line voltages. Okay, and then you can draw. So this is what I draw: the phase voltage and the line voltage. Any question here? Phase voltage and line voltage I draw. Okay, now let me explain you the concept of the operation of full bridge control rectifier. So you see, this is rectifier. This is my positive group. This is my positive group. Number 1, number 3, T1, T3, T5. And here I have my lower group. This is number 2, this is number 6, and this is number 4. Okay. And this is A, this is B, and this is C. So you see, in the upper group, when it is most positive, because this is connected together, cathode is together. So in the anode, whichever is at the highest potential, it will conduct. So that means from here to here, T1 will conduct. From here to here, T2 can conduct. From here to here, T3 can conduct. Okay? Understand? This is my alpha is equal to 0 point for T1. This is my alpha is equal to 0 for T3 point. This is my point of alpha is equal to 0 for T5. So this is the reference for upper group. And this is exactly the same as the half wave rectifier. You see here, this is my, just forget about this. Then this is same as my half wave rectifier. And half wave rectifier, we have already seen this. Understand? This we have seen already. Any question here? No. Now, what about the lower group? Lower group. Look at the lower group. This is the point alpha is equal to 0 for this phase. This phase is what? Phase C. And in the phase C, which thyristor is connected? Tell me. Which thyristor is connected to phase C? T2. And then this is the point of thyristor A. So which thyristor should start conducting from here? What is the reference point? Which thyristor?
T4.
T4. And then this one, T6. Okay. So now you see here, this is T1. The next is T2. The next is T3. The next is T4. The next is T5. And the next is T6. So this will be the sequence of operation for all the thyristors. Thyristor 1, thyristor 2, thyristor 3, thyristor 4, thyristor 5, thyristor 6. So this is the alpha is equal to 0 point for each of them. This is the alpha is equal to 0 point for each of them. Okay. This is the alpha is equal to 0 for each of them. So now we will draw the waveform. But you see here, what is happening? Thyristor 1. Yeah, this is thyristor 1. This is thyristor 1. So thyristor 1 is operating from here to here, can operate from here to here. Yes, it can operate from here to here, from here to here. But you see here, thyristor 1, this is my thyristor 1. So thyristor 1 is operating here. Now from this point to this point. I will divide this in 6 interval. I will divide this in 6 interval. So you see here, from here, T6 has started. This is my 360 degree. One cycle is finished. So it will, this is symmetrical. So T6 is also operating here. T6 is also operating here. T6 is also operating here. Okay. And you see here, T1 is operating from this point to this point. That means 1, 2, 3, 4. So 30 degree to 120 degree. Sorry, 30 degree to 150 degree. And so four like 1, 2, 3, 4 squares. T3 will operate 4. 1, 2, 3, 4. T5 should also operate 4. So this is 1, this is 2. Where the other 2 will go? This is 300. Yeah, 1, 2, 3. And then 1 it will be here for T5. So that means T5 will operate here. From here to here also T5 is operating. T5 is operating. T5 is operating. So from in this house, in this you see in this square, T5 and T6 is operating. T5 and T6 is operating. And then from here to here, what are the thyristors that are operating? Tell me, which thyristor is operating?
Doctor, how T5 and T6 will be operating here?
Okay,
Again?
I will come back to this point. I will come back to this point again. Okay, I will come back to this point again. Let me first start from here. I will come back to this again. Okay, I will come back to you. You will see why it is 5 and 6 is operating. I will come back to this point. Tell me which one is operating. Started operating here. T1 has started operating here. T1.
T6.
Okay, and T6. Yes, T1 and T6 will operate here. Why T6 will operate? And I will come to that point now. And what will be from here to here?
T1, T2.
Exactly, T1, T2. And then from here to here, T2, T3. Yes, because T3 has now started from here. T3 started from here. And then
T3, T4.
T3, T4. And then from here to here,
4 and 5.
T4 and T5. Now you see, each of the pair is operating for 2 squares, means 60 degree. Each of them is operating for 2 squares. Yes. Now what is here? Here you have only one square, because you reach 360 degree. What is operating here? T5 and T6.
T6.
Isn't? So where the other block will go for T5, T6? Here. Because this is the symmetry of the from 360 cycle completed. Yes. So here to here, if you draw like this is T5 to 6. Draw two houses. 2 squares, T5, T6. So this one I have shown here. This 30 degree I have shown here. You see, this is 0 to 30. 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 The same 0 to 30 I have shown here. 0 to 30. Do you understand this point or not yet?
Yes.
Doctor, I did not understand the two pairs, how you choose them to, or how we determine them that both are working at the same time, like two T1 and T6 and T1, T2, how they work.
Okay. Yeah. Okay. You see here. T1 has started working from here. Understand? T1 will switch on here because alpha is equal to 0. We switched on at alpha is equal to 0. So T1 has started working from this point onward. Until what point? Until this point, from here to here. T1 is operating. So we have to check from upper group. T1 is, I told you that one from upper and one from lower will operate at one time. One from upper and one from lower will operate at one point. So from here onward, T1 is operating. But what is from the second group? Negative group. Which one is operating? This is phase B, isn't? This is phase B. In phase B, which one is connected? T6 is connected. For phase B, T6 is connected. So T6 is operating here. From here to here, T6 is operating. You see, each thyristor will conduct for 4 blocks, 30 degree blocks. So this is for 1, this is for 2, this is 3, and this 1, 4 is for, this is for 5. Then for lower group, T2, 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 T2. Then T4, 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 T4. Then T6, 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 T6. Is it clear? No.
Yes, Doctor, clear.
Yeah. So this pattern you have to understand. So now you see, I have now completed the whole cycle. From here to here, T1 to T6, then T1, T2, then T2 to T3, then 3 to T4, T4, T5, T5, T6, then T5, T6. So you can write like this: T5, T6, then T1, T6, T1, T2, T2, T3, T3, T4, T5, T4, T5. So you see 1, 1, 2, sorry, yeah, 1, 1, then 3, 3, 5, 5. Then similarly 6, 6, 2, 2, 4, 4, like this. So let me do it once again, because if you understand this alpha is equal to 0, you can do for all of them. Okay. Do you still you can see this or not? No. You can see the screen?
We can see it.
Yes, look.
Okay. So now you see, I will mark. Please, pay attention. This I am revising. Okay. Repeating the same thing. This is my phase A, phase B, phase C. So this is my reference point T1. This is my reference point for T2. This is my reference point for T3. This is alpha is equal to 0 point. This alpha is equal to, sorry, this is not T2. This is T3. This is T5. Okay, upper group T1, T3, T5. And this is my alpha is equal to 0 for T2, T4, T6. Okay, first I will mark this. First I will mark this. First I will mark this. Clear? Next, what I will do, I will see that you see T1 will be operating for 4 blocks, 30 degree each. T3 for 4 blocks, T5 for 4 blocks. So now you see 3 block is done here. And this is my cycle completed. This is my cycle completed. So this one block is actually here. You see from 0 to 30. So I will show here T5. So here T5 is operating in this. T5 is operating. Then T2, 1, 2, 3, 4 house. Then 1, 2, 3, 4. Then 1. So 1 is only here. So where the other 3 will go? Come back. Here T6, here T6. So T6 will operate from here to here. T6 will operate in 1, 2, 3. Now I will see that in this block T5, T6 is operating. Then in this block, these 2 blocks, T1 and T6 is operating. Then in this 2 block, T1, T2 is operating. Then in this block, T2, T3 is operating. In this block, T3, T4 is operating. Then in this block, T4, T5 is operating. Then in this block, T5, T6 is operating. 1 block only. So the next block is here, from here to here, T5, T6. Do you understand this very well or not? Can you tell me how we mark the turning on the conduction of each thyristor pair?
Yes, doctor, understood.
Okay, next. Now we will see what are the voltages that will come across the line, across the load. You see here. When T5 and T6 is operating, sorry, this is T5 and T6, 1 block. T5, T6 is operating. We have to check what is the voltage when T5 and T6 is operating. So when T5 is operating, this is T5 and T6. So what is the voltage that will come here? Tell me for T5 and T6. T5 and T6.
VCB.
VSC.
VCB. Let me draw it clearly. This is my T1, T3, T5. T2, T6, T4. And here is A, here is B, and here is C. So now T5 is operating. So T5 is operating means this. And T6 is operating means this. So what is the voltage across the load? This point will come here. This is VC. And this point will come here minus VB. So VC minus VB, which is equal to VCB. VCB. VCB is coming. Okay. So I will just map VCB. Next, you see 1 is operating and 6 is operating. 1 and 6. 1 is A and 6 is B. So VAB. So I will you see here, it will go up to what point? There is actually, the angle are not corresponding angle. You have to check. So from here to here, T1 to T6 is operating. So T1, T6 is operating. That means we are getting VAB. This is from where? 30 degree to 90 degree. 30 degree to 90 degree. So 90 degree is my here. So I will map VAB. I will map VAB from here to here. I will map VAB from here to here. Next, what is operating next pair? So next pair is T1, T2. Next pair is T1, T2. So T1 is what? A. And T2 is what? B. So, sorry, T1, T6. T1,
T1,
T2.
T2, and A, VAC.
Yeah, VAC. So this is my VAC for next 60 degree. It will go up to 150. It will go up to 150. 150 is here. Is here. So I will go up to this. Next, T2, T3. So T2, T3 is what? VBC. T2, T3. VBC will go for T2, T3 will go up to 210 degree. Yes, T2, T3. So I will plot this up to 210 degree. And then T3, T4, which is VBA. And then T4, T5, VCA. And then T5, T6, which is VCB. So this is my output voltage, which is shown in red. Do you understand this? Any question here?
Clear, doctor.
Clear. So what is the peak value? What is the peak value here? V line to line peak. Line to line peak. And what is minimum here? You can see what is minimum here. This is at 30 degree of VAB. 30 degree of VAB. So you can check what is 30 degree of VAB. I think it is 0.866 of V line to line peak. This is minimum. So you can find what is the ripple. Peak to peak ripple. Okay. This is the operation of full wave bridge rectifier, control rectifier. But this is currently operating as a diode, because this is, we are at alpha is equal to 0. Alpha is equal to 0 is same as like diode based. It's same as like diode based. Now let us do the same exercise for alpha is equal to 30 degrees. So please tell me, where should I mark? This is my alpha is equal to 0 degree. So where I should mark the operation of
at 60.
Yes. This is the point of starting of T1. Then this is the point of starting of T3. This is the point of starting of T5. Then this is the point of starting of T2. Then this is starting of T4. And this is the starting of T6. Yes. Now, you see, each one of them should operate for 4 blocks. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. So we finished here 2. That means other 2 will be here. So from here to here, T5 is operating. T5 is operating. Got it? Understand?
Yes, and T6 would be below.
Yes. So now let us do the same. You know, because this is very, very sequential thing, you know, very in sequence. And if you understand one, you can just write all of them and draw all of them without any looking at these points, you know. But for now, like to understand, you see how the sequence is coming. For T2, 1, 2, 3, 4 blocks. Then 1, 2, 3, 4 blocks. But you see T6 just started at 360. So all of its 4 block is here. 1, 2, 3, 4. So from here to here, T6 is operating. T6 is operating. Now I will mark the pair. I will mark the pair. From here to here, T5, T6. From here to here, T1, T6. From here to here, same pair you will see. T1, T2. T2, T3. T3, T4. T4, T5. And what is the, now I have to plot in the line voltage. So when you have T5, T6, what is the voltage that you get? T5, T6. VCB. Yes, for T5, T6. It is like this. T5, T6, then T1, T6, then T1, T2, then T2, T3, then T3, T4, then T4, T5. This is, and what you get here? You get VCB. When 1 and 6, what you get? VAB. What you get here? VAC. What you get here? VBC. What you get here? VBA. What you get here? VCA. This is fixed all the time. Now I will plot. First, from 0 to 60 degree, I have VCB. VCB. And then AB up to 120 degree. Then no need to look. You just draw sequentially. Okay. So this is what you get at alpha is equal to 30 degree. Do you understand this? Then next, yes.
Doctor, so everything is basically shifted to the right, right?
Exactly, exactly, exactly. Now put alpha is equal to 60 degree. When you put alpha is equal to 60 degree, you do this, okay? Or do you want me to do one more for you? Do you want me to do one more for you, or you will do it? 60 degrees from where? Let us mark. This is my 60 degree point. Yes. T1, T3, T5, T2, T4, yes, and T6 will be here. Yes, this is your end of cycle. So now you see one more shifting of T5 from here to here, T5. Yes, so T5, T6 is operating from here to here. No, sorry, yeah, T5 for the 3, 1, 2, 3, 4. Okay, and T6 is here. So where is T4? 1, 2, 3. Yeah, 4. Here is T4. Here is not T6. Here is, yeah. T5 is okay. T5 from here to here. T5. But first here you will have T4. And then you will have T5. So first you will have T4, T5. Then T5, T6. Then T6, T1. And then T1, T2. Then T2, T3. And then T3, T4. Okay. So what is T4, T5? T4, T5 is VCA. VCA. Yes. Then T5, T6 is VCB. So we start from VCA. Where is VCA? This one. This is up to 30 degree. And then VCB. And then VAB. Then VAC.
Doctor,
Yes. Yes.
can you mark in the graph, please? Because I got confused.
You want me to explain further?
Yes, about the T4 and T5, T5 and T6.
Okay. You see here, this T5 should operate for how many houses? How many blocks? 120 degree.
For two.
For 4 blocks. Each of them for 120 degree. Yes. Overall, you will see that it will be having like 60 degree pair. Now, this is one house. Okay. Because at this point, you have now finished your cycle finished. So next 3 will be here. 1, 2, 3. For T5. For T5, one block here and 3 blocks here. Okay. Got it? For 4? For 5?
Yes, for 5, okay.
Okay, and now for 4, check. This is 1 block, 2nd block, 3rd block. Where will be the 4th block? In the beginning, from 0 to 30. So from here to here is T4. So first block, you have T4, T5. So first block is T4, T5. Next block is T5, T6. Okay? And when it is T4, T5, you will have VCA. So VCA, I just map on the VCA. This is VCA. You see, this yellow color is VCA. So, and then, so what you see here, now it touches 0. Yes? It touches 0. It touches 0. Now, if you go beyond this, so this is the limiting point. If you go beyond 9 alpha 60, now if you go to 90, what will happen? It will go in the negative direction. It will start going in the negative direction. And in the negative direction, it will go only if you have RL load. If it is R load, it will stop. So this is the limit of R load. This is the limit of R load. After that, it will start giving you 0 if it is R load. Do you follow this point? So draw for 90 degree. Okay, draw for 90 degree. Draw for 120 degree. No need for 150. Okay. So now the 3-phase 6 pulse. Okay. So what you see here, I forgot to tell you that in each cycle you will have 6 pulses. In each cycle you have 6 pulses. 1, 2, 3, 4, 5, and these two together call 1. 60-degree pulse. And how many pulses? 6 pulses. Yes, 60, 60, 60, 60, 60, then 30 and 30. So AB, AC, BC, BA, CA, and then CB together. So this is 60-degree pulse. And this is called 6 pulse rectifier. Here also you see 1, 2, 3, 4, 5, 6. 6 pulse. 1, 2, 3, 4, 5, and then this part and this part together, it makes you 6 pulse. And each pulse is for 60-degree. Each pulse is for 60-degree. Now, the 3-phase 6-pulse bridge rectifier shows a marked improvement in the quality of the DC output over that of the single-phase rectifier. Why? Because you have 6 pulses. In the single phase, you had only 2 pulses. So here the harmonics was second harmonic, most dominant. Here the most dominant is 6th harmonic. 6th harmonic. So you see n is equal to 6 is the first harmonic that is dominant. Next 12, next 18. So harmonics of the voltages are small and at the frequencies that are multiple 6 times higher frequency. So at higher frequency, if you have the harmonics, then it is easy to filter out. You need a small inductor, a small capacitor, okay, a small passive components. This is the advantage of shifting the frequency. So you shifted it 6 times. Okay. So based on this, you have this problem. It says that a 3-phase control rectifier has an input voltage of 480 volt RMS at 60 Hertz. The load is modeled in series RL. Determine the delay angle required to produce an average current of 50 ampere. So the current is given as 50 average. So what will be the average voltage? Average voltage will be 50 into 10, 500 volt. So for 500 volt, what should be the angle of alpha? Okay, so what is the angle of alpha? We can derive the equation. So you see here they have derived from 60-degree plus alpha. They have done it differently. Okay, they have done it differently. I will do it from pi by 6 plus alpha to 5 pi by 6 plus alpha. Now I will derive the equation for you. I will derive the equation. So let us derive the equation. Let us start for VAB. Let us start for VAB. Just I will do for VAB. It will same for all. This is VAB. Okay. So what is VAB? VA is Vm sin omega t. What is VB? Vm sin omega t minus 230 minus 120. When you say when you take VAB, it will be VA minus VB. And what will be the expression for this? √3 Vm sin omega t plus pi by 6. This will be the equation for VAB. This will be the equation for VAB. This will be the equation for VAB. √3 Vm sin omega t plus pi by 6. You can do it graphically by phasor or by analytical expression. Both of them you get this. You know this, yes? Do you know this? That if it is line voltage, it will be phase shifted by, you see, this is my VA, this is my VB. So this is my VAB. This is 30 degree ahead of VA, 30 degree ahead of VA. So this is my expression, √3 Vm sin omega t plus pi by 6. And now I will integrate from here to here, from this point to this point. So what is my integration point? Pi by 6 plus alpha to 5 pi by 6 plus alpha √3 Vm sin omega t plus pi by 6 d omega t. Do this. When you do this integration, you get the expression for the sin omega t plus pi by 6. So this is my expression. √3 Vm sin omega t plus pi by 6 d omega t. Do this. When you do this integration, you get the expression for the sin omega t plus pi by 6. So this is my expression. average voltage, and the expression remains the same. This will be the expression that you will get. 3 Vm line to line by pi cos alpha. This is what you will get. 3 Vm line to line cos alpha by pi. This is what you get. Understand? This is different than how the book has derived, and they have taken different, they have taken, reference as different. They have taken reference as VAB as reference. I have not taken VAB as reference. I have taken VA as reference, and from there I calculated this. Okay. So this is what you get. The expression remains the same. That is 3 into Vm line to line pi cos alpha. This is the average voltage. This is the average voltage. Okay. So cos alpha you can get from here. Cos alpha is equal to V naught into pi upon 3 Vm line to line. This is your alpha. And then you can get alpha is equal to cos inverse of this. So this is what is exactly done here. Okay. How they have calculated. And then for the ripple, 6th harmonics and 12th harmonics. So they got 6th and 12th harmonics from the formula V6 by Z6, V12 by Z12. And what is V6? V6 you get from this 39.4, which is 40 degree. Correspondingly, you get the normalized voltage. And from here, you get V6 and V12. And then you get the current. And then you can calculate the determine the amplitude of harmonics. So they have only asked you the amplitude. So this is how you get any. Do you understand? Do you have any question here? Okay. So we will stop here. And I'll just start your attendance.
Doctor?
Yes.
Regarding today's lecture, it will be included or not in the term?
Yes, it is included. And everything is included.
So Wednesday's lecture as well, or just today's?
Okay, maybe we will limit up to this point. We will limit up to this point. Okay.
Okay.
And we have exam on 8th. Yes. So
Yes.
okay. Next class we'll discuss about your exam because this was important concept for 3-phase because you had to understand this will be asked in your exam also, like what different angle will be given and this graph will be given and you have to plot.
Doctor,
yes.
Is it too much that you included everything? Because I remember you